If a molecule containing both an aldehyde and a ketone, in other words, two functional groups within the same molecule, is reacted with NaOH, an intramolecular aldol condensation can take place to close a ring. And this reaction is particularly effective for closing 5 or 6 membered rings. As you have learned previously, the 5 and 6 membered rings are the most stable ring sizes. So it makes sense that those would be the easiest to close. So for our first example of this reaction, we're going to look at a 1,6 dicarbonyl compound. What that means is it's got an aldehyde at one end of the chain, and if we call the aldehyde carbon 1, you have CH2, 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 CH2. And then you would have another ketone at carbon 6. So if we take this compound and react it with hydroxide, we would end up at the end of the day with a 5-membered ring containing the double bond, and then you would have the ketone exocyclic sticking out of the ring. This compound is generated in pretty good yield, 73%. So what that means is that this is most definitely the favorable reaction pathway for this particular reactant. Well, let's have a look at the mechanism. So the first step is that you generate the internal or thermodynamic enolate from the alpha carbon next to the ketone. There are other enolates that you can generate here. You can generate the terminal enolate from the ketone, or you could also generate the internal enolate from the alpha hydrogen to the aldehyde. Both of those will form. Neither one will get you where you need to go. So that's why this equilibrium with other enolate anions is shown here. It is an equilibrium. You can get to those places, but you will get back to the starting material, and then eventually you will get to the anion that is depicted here. And then that anion is perfectly poised to act as a nucleophile, attack the aldehyde, and close the ring. So remember, the aldehyde is what's going to want to get attacked because aldehydes are the best electrophiles. The ketone enolate attacking the aldehyde is most favorable. If you had the terminal enolate next to the ketone coming in and attacking the aldehyde, that could happen, but that would lead to a 7-membered ring, which is less favorable than the 5-membered ring. So only the internal ketone enolate will lead to the 5-membered ring. Okay, so we've gone through 2 steps of the mechanism. We've closed the ring. Then the rest of the mechanism is that you have the alkoxide anion. It protonates from water. Remember that in a reaction that's done using NaOH, you have water present, and it acts as the proton source to generate the beta hydroxy ketone. And then finally, since you still have OH present, you're going to get base promoted dehydration, and that's going to lead to the alpha beta unsaturated ketone. So the other thing that you might think about is, couldn't this starting material carry out a ordinary garden variety intermolecular reaction? Well, the intramolecular reactions, when you're going to close a 5 or 6 membered ring, are going to be faster than intermolecular reactions because the reactive sites are close together. Okay, especially if you look at this first enolate intermediate, it is drawn here in a suggestive conformation to show that those electrons are right there, poised to attack the aldehyde carbonyl and close that ring. In order to do an intermolecular reaction, the two reactants who are who knows where in solution will have to find each other and collide at just the right angle for the reaction to take place. Okay, so the intramolecular reaction, they're right there, they're poised to do the reaction, and the reaction happens rapidly. As a second example, we're going to start with a 1,5 dicarbonyl instead of a 1,6 dicarbonyl. And in this case, when treating this starting material with NaOH, we're going to get a 6-membered ring. But notice that the ketone in this case is one of the carbons that is part of the ring, as opposed to in the previous example where the ketone was exocyclic. Chemists call this a type 1 aldol, whereas the previous example is what chemists call a type 2 aldol. You don't need to know that. That's just chemist lingo for this. Okay, so how does this happen? Well, I'm only going to give you an abbreviated mechanism since we just did a full-blown mechanism for one of these things on the previous slide, just so that you get a sense of what the key steps are. So your starting material gets deprotonated with NaOH, and in this case now, it is the terminal enolate that is required to form the 6-membered ring. The internal thermodynamic ketone enolate can form, but if it tried to come around and attack the aldehyde, that would lead to a 4-membered ring, which is of course unstable. Okay, so the 6-membered ring has to come from the terminal enolate. So once you form that terminal enolate, I don't have this one drawn in quite as suggestive a conformation, but the nucleophilic carbon comes around, attacks the aldehyde, you break the CO pi bond, and then after protonation, you get the beta hydroxy ketone with the new carbon-carbon bond that we have formed in this reaction indicated in green. Then again, under the reaction conditions, dehydration can take place by removing the alpha hydrogen to the carbonyl, forming the carbon-carbon pi bond, and then kicking off hydroxide as the leaving group, just as we have seen before. Okay, so those are the two different cases of the intramolecular aldol reaction. Both of these cases, it also went on and did dehydration. So that is our survey in several lessons of the aldol condensation. As I've said, it's a very important reaction for organic chemistry, and it is used extensively in the laboratory, and as we've already seen an example of how it is used in biochemistry. So moving forward, as promised, we will now look at what happens when you add enolates to esters, which is the Claisen condensation.